Okay, now we are going to go into the next topic on stability. After we have looked into the closed loop system performance for set point and disturbance, we have to look into the stability of the process. The system not only have to follow the set point and disturbance, but it also has to be stable. And this we're going to talk about how to test whether the system is stable or not to these different criteria that we are going to go through now. The stability of a system is defined as a property for which the output response is bounded for all bounded inputs, which means that if the input is bounded, for the system to be stable, the output also has to be bounded. Bounded inputs are, example, are the step change, which is bounded within certain value, minimum and maximum value. And again, looking at the stability to define the stability criteria, let's look again at the closed loop system here. C is the output of set point U disturbance, and now we want to define the stability of this closed loop system based on some criteria that has been defined in the closed loop. First of all, we get the transfer function as follows. For C with respect to set point change, C with respect to U, we will get this standard transfer functions that we have seen before, and we have all gone through this one before. That the the transfer function, closed loop transfer function, if you put a unit step change at the set point, will be given by this. And if we put in terms of the roots of the characteristic equation here, then we'll get different roots of the equation R1, R2, Rn, where the characteristic equation by 1 plus gs. This is the standard characteristic equation for the closed loop system, which is given by 1 plus g. The stability criteria is defined as if there are any roots of the characteristic equation on the right half of the complex plane, then the response will contain term that grows exponentially in time, and that means system is unstable. Therefore, the criteria of a control system for stability is defined as a linear control system is unstable if any roots of its characteristic equation are on or to the right of the imaginary axis. Otherwise, the system is stable. Okay, we'll look at this location of roots on the complex plane. Why you get complex plane? Because the roots can be either real or imaginary, because it's a polynomial system in the characteristic equation. So we have different locations here. If the roots are on S1, the system is defined as stability criteria is stable on the left hand plane, and the shape of the response is decreasingly exponential decrease. So this is stable system. It's on S2. S2 normally conjugates. It is oscillatory decreasing. Also is stable. It's bounded to stable. If it's on S3 on the imaginary axis, is continuously continuous oscillation. This is just on the verge of stability. This is always the test for stability when it's continuously oscillatory. S3. If it's on S4, it is increasingly oscillatory increasing, which is unstable because it's unbounded. So on S5, it's on the right hand plane, it's unstable. Why? Because it's exponentially increasing. It's on real axis, so it's only one. There's no conjugate. Because X4, they got conjugate. If it's on X6, it's steady, is 0, so it's just continuous straight line. So this location of the roots not only tell us how the system behaves, but tell us the stability of the system based on the stability criteria that we have seen before. Look at an example here. If G1 is given by PI controller, G2 is given by the step tank, and H1 the measuring element given here, then this is the G, which is open loop transfer function, and the closed loop transfer function given by 1 plus G here, 1 plus G. So we will see that the characterization can be simplified to this polynomial here. degree 2, so we got two roots here. So now we want to see the stability based on stability criteria. So we have to check the roots of the equation, which is given by a conjugate roots here, S1 and S2, minus 3 over 2 plus square root 11 over 2j, or S1, S2 minus 3 over 2 minus j, square root 11 over 2j, conjugates, and since both are negative, so they are on the left side of the imaginary axis in a complex plane, and based on the stability criteria, system is stable. So this is the way, based on stability, how to get the stability check by checking the roots of the characteristic equation. The equation defines the stability of the system, 1 plus g, and the location of the root will tell us the stability, and also qualitatively it gives us the shape of the response on the left, how it responds, on the conjugate roots, how it responds, on the right conjugate roots, how they respond, on the real axis, how they respond. You can see the qualitative behavior of the system as well as the stability of the system. So much information is given by the characteristic equation. So this is the first way of getting the roots of the equation. But as you can see, the problem here is what? This is only two roots. If you have SQ, you get 3. But if you have S25, S50, you'll get so many roots. And in that case, it will be very difficult and tedious to get the roots of the equation and to find the stability. Anyone that makes it unstable, the system will be unstable. So with that, there come another criteria given by Ralph, who has come up with the criteria. There's a very detailed analysis on that, mathematical analysis, but it's a simple method of checking the roots of the equation and stability of the system indirectly. And next one we will cover in our next part, what we call Ralph's test for stability of checking the stability of a closed loop system using from the different steps and Ralph's level, which we will cover in our next topic. Thank you very much. Assalamu alaikum.